Thank you. Good morning, everyone. I'm assuming you can hear me and hopefully see the slides.
Yeah.
So I'm going to talk about the work. Thanks. I'm going to talk about the work today that we've been doing with Access Fire, the coupled fire atmosphere model. And we've been working on this for the past few years in a pretty small project, and it's really been proof of concept. And a lot of the conversations that we're having at the moment are really about where we take this capability moving forwards. So here at the Bureau in Australia, there are really two questions that we look at in fire weather when we're talking to the fire agencies and the emergency services agencies. And the first question is about the fire risk on any given day or in any season, which is really about the planning and preparedness, what's going to happen tomorrow, what's going to happen next month, what's going to happen the next fire season. And then the second question is, once a fire has actually ignited and we've got a fire in the landscape, what direction is it going to spread, how fast is it going to move, and what kind of fire behaviour is it going to exhibit? And we're really interested in this study, in this project, on the second question, which is once we've actually got a fire, what's it going to do? And just get the slides to move, bear with me a sec. Okay. So what I've got on the screen now is a photograph of a prescribed burn, fuel reduction burn, which was done at Mount Solitary in New South Wales. And the question really is, can we model the three-dimensional interactions between fire and the atmosphere that you can see in this photograph? Because a fire releases energy, and that energy release actually changes the surrounding atmosphere. So without a fire in the photograph, you're not going to have any cloud there, you're not going to have the smoke, and you're going to have a different wind regime. So you can see at the bottom of the convection column there, you've got convergence from all directions going into the convection column. And without the fire there, you're going to have quite a different wind regime. So the fire has altered the dynamics and the thermodynamics of the surrounding environment. And the question, of course, is how is the new environment with a fire in it different from the unaltered state, and how do the modifications actually change the fire behaviour? So we've been running a coupled fire atmosphere model to look at the fire and atmosphere interactions. There's a number of different coupled fire atmosphere models that are available internationally that are being used mainly in research. And what they've got is an atmospheric component and a fire component. And we use them to investigate the interactions between a fire and the surrounding atmosphere. The model that we're using is Access Fire. Access is Australia's research and operational weather and climate prediction model, and it's been coupled to a fire spread model. And the way that it works, you can see from the schematic down at the bottom, effectively we've got the atmospheric model, so the NWP system, runs a time step. It sends a set of surface parameters, so wind, temperature and relative humidity are the main ones, into the fire spread model, which has got information about the fire fuels, how much fuel load there is on the ground, what kind of vegetation structure it is. The fire spread model runs for a time step. It calculates a heat flux from the amount of fuel that's been burnt in that time step, and it passes that heat flux back to the atmospheric model. Now, once that heat flux goes into the atmospheric model, obviously it changes the surrounding atmosphere, particularly the wind fields, and that's how you get the coupling process that steps forward in time. I won't go into the details of the model structure now, but if you'd like to know more, then there's plenty of information available. So what we've been doing is we've run two case studies as part of the, I guess, the proof of concept project. The first one was on the Waroona fire, which burnt south of Perth in Western Australia in January in 2016. There were 166 homes destroyed, 69,000 hectares burnt, and 2 fatalities on the second night of the fire. Importantly, there were 4 periods of extreme fire behaviour during this event. There were 2 pyrocumulonimbus events, so fire-generated thunderstorms over the fire. You can see one of the photographs on the first day on the bottom right there. And there were 2 evening ember showers. And the 2 evening ember showers happened when you'd normally expect fire activity to decrease in the evening. The first night, the town of Waroona was impacted with significant community impacts. And on the second night, the town of Yarloop was impacted, both in the evenings. And importantly, the fire behaviour that occurred didn't really reconcile with the current risk measures. And that's largely because a lot of the time when we're looking at the traditional approaches to predicting fire spread and looking at fire risk, we're looking at the surface parameters, whereas what happened at Waroona was really interactions between the energy released by the fire and the atmosphere above the surface. So on the left-hand side in this plot, I've got the top the top photograph or the top image shows the fire reconstruction that was done from a reconstruction of the fire information, and the lower plot is our simulation. So you can see there's a pretty good match for the reconstruction and the simulations, particularly when we account for the fact that once the fire hit the coastal plain, there was quite a lot of suppression activity that occurred. So this slide shows really one of the key findings from the simulations, and what it really, the key point is that the fire and the atmosphere interactions changed the surface spread of the fire. So what we're looking at here is a vertical cross section through the fire at the time of the ember shower that impacted Waroona on the 6th of January at about 9 o'clock in the evening. So the top plot shows the fire line in the yellow and purple shading. The brown and the green shading shows the topography. So initially the fire was running on higher ground on a scarp, and then it came down to the coastal plain on the western side. The streamlines show the wind modification near the fire front. So you can see that there's a pretty big difference between the plot on the right and the plot on the left in terms of the streamlines. And the yellow lines show the location of the cross section in the lower plot. So these top plots, the yellow lines are the cross sections that we're looking at lower down. Now, importantly, the left column, the slides on the left show the coupled version. So in the left, the fire and the atmosphere are interacting. On the right, there's no interaction between the fire and the surrounding atmosphere. So the atmosphere doesn't know that there's a fire underneath it. In the lower plots, the pink and orange lines on the topography show the heat flux, the blue shading shows the wind speed, and the lines show the wind streamlines. So the important things to note in here is that, particularly focusing on the bottom left plot, when you've got the coupling between the fire and the atmosphere, the wind maximum is closer to the surface. So without the coupling, the wind maximum is 500 metres plus above the surface. When you turn the coupling on, the fire actually brings the wind maximum right down to the surface, and that's what's driving the fire spread. The wind is also stronger when you've got coupling on, and the combination of the winds being closer to the surface and also stronger, which means, of course, that the fire runs faster and hotter when you've got the fire and atmosphere and interactions captured. What we can also see in this plot is waves in the streamlines, and that's consistent with turbulence being present, and that was obviously a mechanism for the ember showers that occurred and impacted the two towns. So there was mass transport of the embers observed, and we're picking up in the coupling process that there's a mechanism for that turbulence occurring. And obviously without the coupling involved, you don't get that process. So the second fire that we've been looking at was the Sir Ivan fire. This was in New South Wales in February in 2017. There were 55,000 hectares burnt, 55 homes lost. And in this period, there were really dry fuels due to severe drought in the lead up. One of the significant things with this fire was that there was a pyro-CB, a fire-generated thunderstorm, which developed on a synoptic northwest to southwest wind shift during the afternoon. And what we're seeing in Australia is an increase, and internationally in fact, is an increased frequency in these pyro-CB events, or these fire-generated thunderstorm events. And in 2017, the Sir Ivan fire was the first time that we did an accurate pyro-CB forecast in Australia. So the first time it was seen was 2003 in the Canberra fires, and by 2017 we had some skill in prediction, and in the last fire season, which I'll talk about a bit more in a minute, we obviously had a lot of practice in pyro-CB forecasting. So Access Fire, the coupled model, you can see on this slide, actually produced a pyro-CB over the Sir Ivan fire on the wind change, which was when it occurred. And the processes and the dynamics of it seem to be a pretty good match for what we have in terms of the observations and the simulations. And what we found was that adjusting the surface fuel loads, which obviously changes the heat release, the more fuel load you've got, the more heat's released, the less fuel load you've got, the less heat is released. It showed that in the simulations, in the model framework, we're actually really close to the threshold for go, no go for pyro-CB development. So the boundary layer settings in the model are around about right for generating deep moist convection over a fire. So there's a huge amount of interest in Australia in deep moist convection over fires. And what Access Fire now gives us is the capability to explore these processes in more detail. But one of the things that we've really recognised, particularly from the last season and some of the fire events that we saw, was that pyro-C is an indicator rather than a precursor to extreme fire behaviour. So if we've got pyro-CV, we've obviously had extreme fire behaviour happening at the surface for some time. So what we can do is use the coupled model to explore the continuum of processes that are occurring. So last season, our fire season 2019-2020, it really was an indicator of the future fire risk in the changing climate. And this isn't just an Australian challenge, it's obviously an international challenge. We're seeing changing fire regimes around the world. And what we're seeing here in particular is an increased demand for accurate and timely fire predictions and fire simulations that can be passed to the community during these events. And in the past few years, I spent a lot of time talking to various community forums, including on radio and various presentations. And I think one of the things that's really quite noticeable is that the science that we're doing around fire and atmosphere interactions really resonates with all of the community, because people can see the processes occurring when they're looking at the photographs and the imagery in real time. So what I'd like to talk about now is 3 of the fires that we're going to look at next from last fire season. The first one was the Badger Fire in New South Wales. It did an overnight fire run of 36 kilometres with deep flaming, and there were media reports of extreme fire behaviour in the middle of the night, including a vortex with tornado strength winds. Now, fires are meant to lie down overnight, but the black and white photograph, which was taken from an aircraft just before midnight, shows that this fire didn't lie down overnight, and we had extreme fire behaviour through the overnight period. And part of the reason for this was that there was a heat wave for several days. It was a 3 or 4 day heat wave. And you had a really shallow overnight inversion. So on the bottom right here, I've got the trace from the F-160 from Nowra, which is near the coast, the closest station to where the fire was. And what you can see in the plot is that we've got this really, really shallow inversion showing up on the trace. But of course, the fire was releasing a phenomenal amount of energy. So it mixed out the near surface inversion, and the fire was effectively running in a daytime boundary layer in the middle of the night. And what this led to was a significant discrepancy between the official forecasts that had been issued and the observations near the fire site. So there was a more than 10-degree error in temperature. And this isn't because the forecast was wrong, it was because the NWP model was doing what it's meant to do, which is produce an overnight surface inversion and set some decoupling overnight. But the fire's energy is just mixed straight through it. So it really shows why we need to be looking at the interactions between the fire and the atmosphere in the predictions. On the top right, I've got a cross section through New South Wales, or southern New South Wales at the fire. And what you can see in here is that there was a lot of wind above the surface. So about 1,000 metres, about 1 kilometre above the surface, less in some points, you had 40 plus knots of wind above the surface. And obviously that was what the fire plume was mixing through in the overnight period and bringing that wind down to the surface. Now, in terms of impacts, there were significant community evacuations in the overnight period, so people were evacuating homes in the dark, and we also had fire crews battling extreme fire behaviour in the dark. So that really highlights the impacts of these sorts of events. One of the other fires that we're going to be looking at is the Kangaroo Island fire, which is just south of where I am now in South Australia. So lightning ignition started a number of fires that burned for several weeks. Over half of the island burnt, and many of you would have seen on the international news that there were significant impacts to the native wildlife and the vegetation on the island. The main fire run was with a synoptic change on the 3rd of January, and a reconstruction that was done of this fire by one of the best fire behaviour analysts in the country. It couldn't reconcile the direction and the speed of the surface fire spread with the surface winds. And the reason for that, of course, is that the fire wasn't just being driven by the surface winds, it was being driven by the winds above the surface, which were quite complex as the synoptic change went through. And you can see from the bottom right plot, which is showing us wind observations from 3 of the sites on the island. You had quite a lot of complexity in the structure and the speed of the surface wind change, which was reflecting, of course, the winds above the surface. So what we're expecting is that when we run the coupled fire model, we'll start to see some of those processes in terms of the mixing down being resolved by the model. One of the other things we want to look at from last season is fire-generated vortices. Now, fire whirls happen all the time on fires, but what we saw last season, not just in Australia but also in the United States, was several fire-generated vortices or fire whirls or fire tornadoes, where there were tornado strength winds more than 300 kilometres an hour. Now, obviously, these kinds of phenomena are a real hazard to firefighters because, in part, they can actually form and move ahead of the main fire front. So they can track kilometres ahead of the actual main fire front, and they have resulted in fatalities at a number of fires. Some of the ingredients are known. We did a report on one of the incidents here in Australia, and what we've got on the right is a schematic that we've produced for communication to the fire agencies about what some of the ingredients are that contribute to these things forming. So one is an intense fire burning up a lee slope, obviously heavy fuels, a lot of energy release. You can't have too much ambient wind, so there's a sweet spot in the ambient winds. If you've got too much wind, you've got too much shear, so it blows the top off the vortex formation. If you've got the winds that are too light, then you don't have sufficient wind for it to form. Lee slopes are favourable because you've got the low level wind shear, which helps spin up these things. And where you've got embers starting new spot fires, obviously as well, you've got another mechanism for local wind shear. And one of the key things seems to be consistent across a number of events is that when you've got rotation in the main convection column above the fire, then you've got a pre-existing part of vorticity. And also where you've got a really strong updraft, you've got the stretching component for the vortex formation. So what we're hearing from the fire agencies is that because of the impacts of these fire-generated vortices, there's really a need to develop predictive techniques. And what we know is that we can resolve these vortices in LES models, and we can also resolve vortices in access fires. There's the opportunity to do more research in that space. So just in conclusion, there's the links between what we're doing in research and what we're doing in the real world. And I spent most of last season working in the various fire agencies around the country, providing briefings and interpretation. And that really provided insights for me into how we link some of the research into the real time. In meteorology, as operations or doing research, we really use a combination of conceptual models and scientific evidence. So there's this pattern recognition from what we've seen in the past in terms of the conceptual piece, and also what we're seeing in the computational model output. And that really provides us the evidence piece for the communication. But in the fire agencies, they're very process driven, they're very systems driven, and documentation is really important. And particularly in these higher end events, there has to be accountability for the decisions that are made. But overwhelmingly, it's not models that are making decisions, it's people that make decisions, and those decisions have to be evidence-based. And that's where I see there's this huge appetite from the agencies to see models like, or capabilities like Access Fire translate into an operational piece so they can be used for decision support. So I've talked about Access Fire, our coupled fire atmosphere modelling capability, which looks at the fire interactions. The simulations have really helped enhance our scientific understanding of what's happening in the fire and atmosphere interaction processes, and that's in part because it's really difficult to take observations in a fire environment. And there's an increasing need and appetite in our fire agencies and also in the meteorologists for more use of this kind of tool, because we're seeing increased fire impacts in a changing climate. And we need to have the robust and the science-based tools to inform the warning messages, and in particular the community response. Thank you.
Thank you, Mika. Very nice. We have just time for one question about verification performance of the coupled fire weather prediction system. How are you verifying the performance?
Yeah, good question. So far, because it's really been proof of concept, we've only run it on a few cases. So we haven't been doing systematic verification. It's been quite subjective. So what we're doing is matching what we're seeing out of the model with the fire perimeter, and that's tended to vary a little bit depending on what fire model's in there, but we've had really good results with one of the model. So that's sort of the first step. The second thing for me is that I've been working with the coupled fire atmosphere modelling for about 10 years now, and spending a lot of time talking to fire agencies and people who are out on the ground. And again, subjectively, we're seeing a really good match between what the results are showing in the model and what people saw on the ground that they couldn't explain or didn't match traditional approaches to fire prediction in real time. So we definitely need to do more formal verification as we progress with the model. That's one of the things that we'd like to do. Obviously, that takes time and resources, but from the information available, we're really seeing very good subjective results in terms of what happened on the fire and what the model's producing.
Right. Very good. It sounds like your involvement with the fire agencies is part of the process of developing trust, and they seem to trust your interpretation. And you're at this point, you're very key in the process.
Yeah, definitely. And that's one of the things. I mean, here in Australia, we've got a great relationship between the Bureau, the Met Agency, and the Fire Agency. So one of the challenges is, obviously we understand a lot of these processes subjectively in terms of how the weather and the fire in 3 dimensions and in time evolution is impacting the fire. But we really need to embed what we understand subjectively into quantitative methods that fit into their decision process in order for it to be robust and repeatable moving forwards, and moving away from a person interpretation, which is obviously useful and where we're at the moment, into a repeatable product.
Right, right. Excellent. Very good. Thank you very much, Mika.
Thanks.
Given the time, we were only 5 minutes late. We were slow starting a little bit, and we're actually on time. So I would like to thank all the speakers for some very interesting, and they were all excellent presentations. Unless Jenny has something more to add, I would like to thank everybody for participating. I would like to thank the colleague from Bangladesh, who it's 3 a.m. in the morning or something, 4 a.m. in the morning, for participating. So these high weather seminars are very well attended by the globe. So thank you very much. I think we'll end it at this point. Thank you.